Welcome to the next lecture, which is a follow-up to the introduction to systems of linear equations. But now what we want to do is get, into the seriousness or serious business of solving systems of linear equations. As we said before, solving here stands for making the unknowns known. Okay, so let us recall first what is a linear system. Okay, so we said a linear system with n unknowns and m equations has the following form. In general, has the following form: a11 x1 plus a12 x2 plus a1n xn equal b1, and then a21 x1 plus a22 x2, etc. b2, and then the last equation will be am1 x1 am2 x2 amn xn bn. And this linear system, to it we associate in a natural fashion what's known as the augmented matrix, because it has all the information matrix. And you will see later on, okay, we will say something about that this augmented matrix can be programmed, not the system in the way that you see it right here, but we can program an augmented matrix to somehow help us solve this linear system. So this is very important when you are dealing with, for example, large number of unknowns, like in economics, as I said before, or sometimes in some numerical applications where you end up into these systems that are very large. Okay. When we do some approximations, numerical approximations, and so on and so forth in differential equations and PDEs. The point I want to make is that all the programs that you can implement in computer programming for solving linear systems, they rely on these augmented matrices. Okay, there is no need for us to write this equation. It doesn't make sense. But for the augmented matrix, the same operations we are going to do, the same manipulations we are going to do to the system can be done on the augmented matrix, and it will help us. And we'll see this. Okay, we'll see this a little bit later on. So the augmented matrix is given by what? So remember, we need a11, the coefficients, a12 all the way to a1n, and then b1. We need the non-homogeneous term, a21, a22, a2n, and then b2. And at the end we have at the bottom, the last row will be the coefficients of the mth equation, 2 a mn, and then bn. So this is the matrix, and to separate between the coefficient matrix and the augmented matrix by adding the non-homogeneous terms b1, b2, bn, that's the last, bm, the last column. So we add this bar to separate, just to separate between the coefficients and the non-homogeneous terms that we have in the system. Okay? So now, what is the concept of a solution? As we said earlier. So we will say that S1, S2, these are numbers, Sn is solution if and only if x1 equal S1, x2 equal S2, and xn equal Sn satisfy, okay, all equations. If one of them is not satisfied of the system, then you don't have a solution, or it's not a solution. So you see here, this goes into what? For example, if you are asked to check if a set of numbers is a solution, it's a lot easier. It's a lot easier because we just plug it into the system of the equations and see if they are satisfied or not. and then we decide the answer is yes or no. So here, first of all, pay attention that I gave you here an ordered set of numbers, because if I say 1, 2, 3, 4, 5, okay, which one is x1, which one is x2, which one is x5? So you have to put an order, so I will know that the first number, s1, is the first unknown, so I will plug it into the first unknown, etc., etc. So you need to have that kind of order in these numbers. You cannot tell me just check that 1 and 2 are is a solution. No, I cannot do that. Which one is 1 and which one is 2? Okay. Anyway, so as we said earlier, so checking if solution or not is easy, very easy. But finding all solutions, that's very hard. Okay, so solving is the same. So sometimes people would say find the solutions to a system or solve the system. Commonly used. I mean, it's not like one eliminates the other one. We can do the same. Okay, so this will become our goal. This is the goal. Goal, okay, is finding all solutions. Finding all solutions. Of course, if any. I mean, we don't claim that any system will have solutions. It may not have. We'll see on some examples. But this is basically the goal that we are going to be working on. Okay? So let me start with a simple example, just to illustrate this. Okay? Example, beautiful example, which is the case of 2 by 2. So let's say systems where n is equal to 2, m is equal to 2. So we know in this case we are dealing with a1x. There is no need for a11, etc. Just two equations, plus, and also x1 and x2 become just x and y. b1y equals c1. a2x plus b2y equals c2. Okay, so here, for the case of two unknowns with two equations, we can use a little bit geometry, okay, in this case, just to help us illustrate what's going on here. And we can look at the plane R2, okay, where x and y are just the coordinates of a point. So we have the x-axis and the y-axis, and the point is x and y. Okay, so that's the pair xy. Okay, so we can use this interpretation to help us understand the concept or the goal of finding all the solutions in the case of a system which is a 2 by 2. So keep in mind, it's just to help us understand what's going on. It gets complicated when we go for large systems, okay? It gets very complicated. Okay, so now, of course, we're not going to assume that A1, B1, C1 are all equal to 0. Otherwise, if 0 equals 0 is useless. We really need to see the equation other than 0 equals 0. So for that reason, we are going to assume that A1, B1, and C1 are not all identically 0, as well as A2, B2, C2. If they are not A1 and B1 both equal to 0, then both. So in this case, what we have here is lines. What we have are, this is geometric line, the equation of a geometric line. So what we have basically are two lines, okay? And x and y, the solution, is just a point, okay, that belongs to line 1 and line 2. In other words, is the intersection of two lines. Okay, so if that's the case, how does it look like the intersection of two lines? Okay, so let us go again. So we have here, first case, something like this. So we say non-parallel lines. So one line is like this, and the other line is like this, non-parallel line. Okay, what about if we go now for parallel lines? Okay, parallel lines. So in this case, what we have is two cases. Either we have this, and the next one is this, parallel, huh? Yeah? And finally, the third case, and the last one is that we have the two lines which are parallel, but, okay, and the other one is parallel but the same. So now let us discuss the intersection between the two lines. What happened? So in the case, in this case here, we have a common point is this point. So there is only one point that's common to the two lines. In other words, the system, in this case, system has one solution. Only one. Okay? It's only one point that satisfies both equations. Okay, what about the second one? This is the first one. What about the second one? And this is the third one. So in the second one, the two lines do not intersect, and therefore the system has no solution. And the third one, here, the two lines coincide. It means that the two equations are the same. Okay, basically, so basically the solutions are the two lines. So you have infinitely many what? So here the system, every point on the line, okay, is a solution. So here the system has infinitely many solutions. So this is really interesting. Why? Because what does it mean? It means that a linear system, at least in the case of 2 by 2 with two unknowns in two equations and two unknowns, what it says is either you have no solutions, one solution, or infinitely many solutions. For example, it does not make sense. There is no way that we can find a linear system 2 by 2, okay, two equations with two unknowns that has two solutions. You can't. It's not possible. Okay, this is interesting, because things start to give us some hint on the inner working of these linear systems. Okay, it gets complicated. Now, what happened to 3 by 3? Similar. Why? Because 3 by 3, we are going to have now a geometry in R3, because every equation will represent what? A plane. And then we are looking at the intersection of planes. And I'll leave it to you to see that it's exactly similar conclusion than what you have here. Meaning what? Because we are only looking at the solutions. So either you have what? One solution, no solutions, or infinitely many solutions. It's very, very interesting. So this is just to give us a hint of what the problems that we have will get us in terms of the general case of systems, linear systems with n unknowns and m equations. So before I move on, let me just say something here, a new definition. So that we will have to, a new terminology, we will say definition. Okay, so a system, a linear system, is said to be consistent if it has a solution. Otherwise, we say it is inconsistent. So remember, it's just terminology. I mean, let's not focus on the words. At the end, you will have a system and you have to solve it. That's it. As an engineer, in all applicable matters, it's just, you have a system, solve it. So what I'm trying to say is that these two words, consistent, inconsistent, it just tells us what? That whether we have solutions or we don't have solutions. In general mathematics, we call that an existence problem, okay? So we have solutions or no solutions is existence problem, okay? So if you have solutions, you are consistent. If you don't have solutions, you are inconsistent. Now, whether you have one solution or more than one, that's known in mathematics as a uniqueness problem, but that's another issue. Anyway, so here we are. So now we are ready. So we're ready now to reflect on the general case. We saw on this simple example of 2 by 2 what to expect, okay? Now, what happened when we go for the large systems, any system, okay, with n unknowns and m equations? What's going on? What happened? So we have an idea. This is an old idea, by the way. It's not like fairly recent. No. This is a very old idea, which is amazing. I will tell you in a few seconds why. Is the fact that let us start with equivalent is known as equivalent system. So what's that? Okay, so two systems, two linear systems are called equivalent if they have the same solutions. So remember, what's the goal? Okay, the goal here is, given a linear system, find the solutions. Okay, so what if I tell you that these two systems, they have the same solutions? So in this case, I just focus on either one of them. Okay, I can choose this or this because the goal is to find the solutions. As long as the goal is to find the solutions, and I know that the two systems are equivalent, then you can work with either one of them. That's the idea. That's the power behind. This is fundamental, okay? So now, how are we going to use this? It's very simple. I mean, it's not like equivalent in the sense of the goal, because in mathematics, equivalent can be used in different understanding and different contexts. But in the case of linear systems and our main goal, which is to find all solutions, that's why we're using this concept of equivalent system. Okay, so now let's say, for example, we have this terminology and now we have a given system. Okay, so given a system, what we want to do now is there a way to find a system which is equivalent to the original one and easier to solve? So now you see the goal has changed now. So here, new goal. Beautiful goal, by the way. So given a linear system, find, so this is a new goal, find another equivalent system, linear of course, which is easier to solve. Wow. So how are we going to do this? So the people, they thought about this from day one, a long time ago, okay? And they started playing with a linear system. So let me explain exactly what these people did. Ready? It's really simple, okay? Not complicated. So let's call them elementary operations. And they are really elementary. Okay? So let me start with 2 by 2 to illustrate what I'm going to be doing. Okay, so consider a system with n equals 2, m equals 2. So we have 2 unknowns and 2 equations. And for the sake of argument, let us write them as E1, the equation of xy equal b1, and E2 of xy equals b2, the 2 equations. Okay, so now we're looking for all the x and y's that satisfy both equation E1 and equation E2. Yes? Okay. What if I take now, look what I'm going to do. I'm going to take E2 of xy equals b2 and E1 of xy equals b1. So what did I do now? I took my system and I changed the order of the equations. The first equation becomes the second equation. The second equation becomes the first equation. Clearly, it will not affect x and y. If you satisfy the 2 equations in the first one or the second one is exactly the same. So these 2 systems are equivalent. So these 2 here are equivalent. Yeah? Excellent. Now, what about if I go, let me put it with a different color. So this one with this one, okay? They're equivalent, okay, the 2. Okay, what about now if I do the following? I take the first equation and I multiply it by a number, non-zero. So we say C1 times E1 xy equal C1 b1 and E2 of xy equal b2. So multiplying an equation by a number, non-zero. So it's very important that C1, not C1, let's not call it C1, just a constant, okay? So C not equal to 0, okay? Then the 2 equations are the same. Why? Because I can multiply by 1 over C. That's why we need it not to be equal to 0 and go back to our original what? Set of equations. So in this case, obviously, these 2, this and this, are again equivalent. So again, if I change the order of the equations, equation 1 becomes 2, 2 becomes 1, no problem. 2 equations, you change them from their positions, you have nothing will happen. It will stay equivalent. Okay? If I multiply one equation by a constant not equal to 0, no problem. And finally, what if I have E1, the first equation, that's fine, I don't touch it. But what I do, I take E2, the second equation, and I add to it a constant time the first equation. Be careful, because you have the B1 and B2, it's the non-homogeneous in general. So it will be B2 because of E2 plus the C times B1. Okay? So it's very easy to see what? That if I take now the second equation, the new one, minus C E1, it's going to bring me back to my original equation E1. Okay? As well as E2. So I have E1, but the E2 I can still generate it by doing what I just said. Okay? I can do the inverse operation. So in this case, these systems are all equivalent. You can do these operations and having, and being all equivalent. So this one, okay, with this one are equivalent. Okay, so these are simple operations on the equations, okay, and we can apply them, and every time you apply these 3 simple operations, what you generate is an equivalent system, and you keep going. In other words, I can apply them over and over again, and every time I get what? A new system which is equivalent to the previous one, which is equivalent to the previous one, till I reach my original what? System. Okay? So let us illustrate this, okay, operations on a simple example. Okay? So let's go. Example. So it's going to be long. I don't want to take a simple example, very simple. I'm going to take, I'm not taking a 2x2. I'm going to take a long one, okay? So I'm going to take a 3x3 to illustrate it, and then we go back again and say something about the augmented matrix. I wanted to show you how you can program it, okay? So let's start first the following. Solve, okay, x plus y plus 2z equal 9, 2x plus 4y minus 3z, 1, 3x plus 6y minus 5z equal 0. Okay? So basically find all solutions, x, y, and z. Okay, at this stage we don't know. Do we have some solutions or not? Consistent, inconsistent? And if we have consistency and we have solution, do we have one or plenty? Okay, remember I told you linear systems is either one or infinitely many what? Solutions. Okay, so now we want to do these elementary operations to illustrate how, because clearly elementary operations, clearly the system that you see here is not easy that you can guess what x, y, and z are. I mean, we are not in that business, because yeah, you may try these whole numbers 1, 2, 3, 4, 5, 6, 7, but in all practical matters the numbers are ugly looking, and therefore do not expect in real life when you're doing, and all the numbers are not like 1, 2 that you see here, 2, 4, minus 3, 3, 6, and minus 5. No, and 9 and 1. They can be extremely what? Awfully complicated, okay, and ugly looking. So anyway, so we need to learn a technique that works all the time, okay, that works all the time. And these elementary operations are very, very beautiful. Okay, so this is what we are going to do. Okay, so let's go and keep x plus y plus 2z equal 9. And look now what we're going to do. We're going to look at the second equation. We have 2x. And I want to get rid of the 2. Okay? 2x. So what I'm going to do is I'm going to take e2, the second equation, minus 2 times the first equation. Okay? So that's the third operation we talked about. Huh? So what's going to happen when I do that? Huh? So the second equation minus 2 times the first equation. So this will give me what? 2x minus 2x, 0. So x is gone. Good. And then we have 4y minus 2y. That will be 2y. And then we have minus 3z minus 4z minus 7z equal 1 minus 2 times 9, which is 18. 1 minus 18, that's minus 17. Okay. Now pay attention to the third equation. I can keep it and then do one operation at a time. Okay? One elementary operation at a time. Okay, so let's do it anyway. That's fine. But I can also do 2 operations at the same time. Okay? So now let us get rid of 3x. So by using the first equation. Okay? So remember, by the way, that this new system is equivalent to the previous one. Because once you perform only elementary operations, you preserve the solutions. Okay? So x plus y plus 2z equal 9. 2y minus 7z equal minus 17. And now we go. The last one, okay, minus 3 times the first one. So we will get what? 3x minus 3x. That's where we did it. Gone. 6y minus 3y, 3y. And then minus 5z minus 6z minus 11z equal 0 minus 3 times 9, that's minus 27. Okay, so you have to be careful about your algebra. Your elementary algebra can be really a drag. I mean, if you are not careful in your algebra skills, with your algebra skills, then this will not work. Okay, so you may be in trouble. Okay, great. So now pay attention that x is gone from the second equation and the third equation. Okay, now let's now do the following. Let us divide the second equation by 2 or multiply by 1/2. Why? Because I want to have y. So this gives me what? X plus y plus 2z equal 9. Y minus 7/2 z equal minus 17/2. And then 3y minus 11z equal minus 27. Yes? Why? Because I want to have that number 1 to help me. Okay, and you see it coming, huh? Now what I'm gonna do? So now what I'm gonna do is first preserve the first equation. And now what you do, keep the second equation. And now to get rid of the 3y, I'm gonna take the third equation minus 3 times the second equation. So it's gonna be 3y minus 3y is gone. And then you have what? Minus 11 plus 3 times, because again it's minus 3 times minus 7/2, so it's 21 over 2 times z equal minus 27 plus 3, I'm sorry, is that what I did? Yeah, times 17 over 2. Okay, so what is minus 11 plus 21? That's minus 1/2. So let's put minus 1/2. Okay, minus 1/2. Okay, and then we have to do the algebra, and you will see that this is all equal to, okay, this is all equal to minus 3/2. Okay, okay, so now let us continue. X plus y plus 2z equal 9, y minus 7/2 z equal minus 17/2, and now we have, clearly I'm going to multiply by minus 2, and this will give me z equal 3, right? So let me just stop for a second here. What did we find? All the systems, the original one and this one are equivalent, okay, via these elementary what? Operations. And as you can see, I found in this system, the last one that you see here, z equal what? To 3, right? So there are two ways. Either you go and you plug it in the second equation and you get y, okay? Meaning that y minus 3 times 7/2 equal minus 17/2. And this will give you whatever for the value of y. And then once you found z and y, you plug it in the first equation and you find x, okay? I'll come back to this one later on, okay, to this system. But why do we have to stop here? Let us continue, okay? And let us continue with elementary operations. So x plus y plus 2z equal 9. And then what I'm going to do is get rid of z in the second equation. So I'm going to multiply the third equation by 7/2. 7/2 and add it. So I will find y. But if I add 7/2 z from the third equation with the minus 7/2 z, it's going to go away, and I will find what? That 7/2 times 3, 21 over 2, minus 17/2. Okay? And that will be 4/2, and that will be 2. And then z equals to 3. Okay? Now, I can also get rid of z between the third equation and the first equation. So what I'm going to do is take the first equation minus 2 times the third equation. I'm keeping now with this elementary what? Operations over and over again. So I went down all the way to z, I found it, it's equal to 3. And still I keep going up now, and then let's get rid of the 2z. So I'm going to take the first equation minus 2z, the first equation. So it's going to give me x plus y, and 2z minus 2z, 0, equal 9 from the top equation, minus 2 times the third equation, which is 6, which gives me what? 3. And we have y equals 2 and z equals 3. And now let me get rid of y in the first equation, okay? So I will get what? First equation minus the second equation, which gives me what? X, y minus y is gone, equal 3 minus 2, 1. And then y equals 2, and then z equals 3. So you see, through these elementary operations, I am able to find x, y, and z. So obviously, the last system has only what? One solution. So the original system has one solution, which is 1, 2, and 3. Okay? So how does it translate into the augmented matrix? So these are, so when we go to the augmented matrix, these elementary operations on the equations, they become what? They become elementary operations on the rows, because every equation is in fact a row in the augmented matrix. So what we have, same idea. You can interchange two equations, you can multiply an equation by a constant, and you can add to an equation a number time another equation. So these operations, they become what's known as elementary row operations. So the elementary operations on the system, on the equations, but they become just elementary operations on the rows. Okay? So here, so what are these elementary the elementary row operations? So let us go back to the example that we just did. Okay? So if we go back to the original system, the equation was, the augmented matrix was 1 x plus y plus z, 1, and 9 is the non-homogeneous term. The second equation was 2, 4, minus 3, and then 1. And the last one is 3, 6, minus 5, and 0. Okay? So this is the augmented matrix associated to, let me take you back, to the original, this one here. Okay? The original system. Okay. So now, all the examples I described, all these operations, okay, let us see how they translate into the, I'm going to put them one by one, okay? So, first, what did we do? Okay, so we got rid of the 2 in the second row. So we took the second row minus 2 times the first row. So we kept the first row, and then 2 minus 2, 0. 4 minus 2, 2. Minus 3 minus 2 minus, I'm sorry, it wasn't, it was x plus y, I'm sorry. It was x plus y plus 2z, huh? Plus y plus 2z. So the coefficient of z is 2, not 1. Sorry. So here we go back and we correct. So when you take 2 times 2, that's 4. Minus 3 minus 4, minus 7. And then we have 1 minus 18 minus 17. And then we have 3, 6, and minus 5, and 0. Okay, so now let's get rid of the 3. So what we'll do, we'll have 1, 1, 2, 9, 0, 2, minus 7, minus 17, and 3 minus 3, 0, 6 minus 3, 3, minus 5, minus 6, minus 11, and then 0 minus 27. Yes, and that's what we have. right? Next, what did we do? We divided by 2, okay? So 1, 1, 2, 9, and then we go 0, 1, minus 7 half, minus 17 half, and then 0, 3, minus 11, minus 27. And then what did we do? We took 1, 1, 2, 9, and then we go 0, 1, minus 7 half, minus 17 over 2. And now we go get rid of the 3 under the 1 in the third equation. So the 3 becomes what? 0 minus 0. We'll multiply the second equation by minus 3, and we add it to the last one. So minus 3 plus 3, 0. Minus 3 times 7 half is 21 over 2, minus 11. And this will give me minus 1 half. And then the other calculations will give me minus 3 half. Okay? So once you have done that, we will multiply. I don't want the minus 1 half. Let's multiply by minus 2. That's what we said. And we get 1, 1, 2, 9, 0, 1, minus 7 half, minus 17 half, and then 0, 0, 1, multiplied by minus 2, and then 3. Yes? Great. So now, at this stage, I want you to pay attention to the matrix. Look at the matrix. It's what's known as a triangular, upper triangular matrix. You have zeros under the diagonal of the coefficient matrix. So technical names, okay? But that's where we are. So now what we are gonna do is keep going. So remember at this stage, we were here. We found Z. Remember what I told you? Okay? You are here. This one here, right here. This one. So this one, you found Z. So basically, if I have Z, I can go back and get Y, and then I can get X. But what we are gonna do, we are gonna keep going, okay, with these elementary row operations. Yes. So now I'm gonna use the one at the bottom to get rid of the 7 half. So I'm gonna take 7 half times the last equation plus the second equation. So I have 1, 1, 2, 9, and then 0, 1 plus 0, 0, and then 7 half times 1 plus 7 minus 7 half, 0. And then we add this, and then we'll find that it will give me what? It will give me 2, and then 0, 0, 1, 3 when I do the algebra. Okay, so the second equation becomes y equals 2. Okay, and now let's get rid of the 2. Okay, so this will give me 1, 1, 2, 9, and then 0, 1. Oh, I'm sorry, I forgot. I'm sorry, because I am using, okay, the last equation to get rid of the 2 on the top, okay? So I'm going to multiply by minus 2, add it to the first equation. So this will give me 0, 9 minus 6, 3, and then 0, 1, 0, 2. I will not touch the second equation, nor the... and now I'm going to use the second equation to get rid of the second one, okay? So I will get the second equation, 3, here, 1 minus 0, 1, 1 minus 1, 0, 0 minus 0, 0, 3 minus 2, 1, 0, 1, 0, 2, 0, 0, 1, 3. And as you can see, this is the augmented matrix of the last system. Okay, so where do you see the solution? You see it in right here. So you see, we added, so if you write the system associated to this one, okay, we will find that the system becomes x equal 1, y equal 2, z equals 3. So you see, it's the best that you can hope for. So my point is, through these row elementary operations, or row or the elementary operation on the equations, either you do it on the system or you do it on the augmented matrix, you can what? Generate a simple system at the end that will have the same solutions as the original one. Okay. So before I finish this lecture, let us again go over the concepts that we learned in this one, and let me do it in red. Okay, so what are the new ones that we learned here? Number one, we are talking about what? Solving. The key here word is solving linear systems. So this is now very important. What else? Consistent and inconsistent systems. Number three, equivalent systems. Number four, elementary operations. And here, of course, you have two types of elementary operations on the equations of the system, or elementary row operations. And this one, we applied them to the augmented matrix. Okay, so this is what we are learning, what we learned in this lecture, and in the next one we'll talk more about this technique that we saw here through these elementary operations or elementary row operations. And as I said before, this is an old technique, and what's amazing is its applications in numerical implementation. It's really amazing.